Welcome to the next lecture on electrical machines 1, and if you recall, we have been discussing about the armature reaction in general, and then how to get rid of the effect of armature reactions in our last lecture, both for motor and generator mode of operation. And this lecture was important, and please try to go through it carefully. And there also I told that a coil which is undergoing commutation will get affected by the quadrature axis flux, and therefore, for generator I can put some interpole, thin poles on the quadrature axis, that is where the brushes are placed. Current changes from dot to cross. Polarity of the pole should be same as main pole ahead, because south pole is positive. So, here some positive pole you have to nullify it, and sometimes the strength of this pole is slightly made higher. Not only it compensates, but gives you a negative flux like north pole here, in order that the conductor starts getting the feeling of what is ahead, the generated voltage wise. So, it improves commutation, and these are the thinner pole. And the important point is, if you have done it for a generator mode, only thing you do is the same diagram can be used as a motor pole, as a motor description of different fluxes, like no load flux because of field current, armature flux. Simply reverse the direction of rotation. So, for generator mode from left to right, and for motor mode the speed is right to left. And as you can see, in case of generator mode, the polarity of the interpole should be same as main pole ahead, but in case of motor mode, the direction of rotation is like this, right to left. So, this is the the conductor moves, the polarity of this, of course, interpole remains same. So, it is same as main pole behind, which is leaving behind. This you must understand. So, in today's class, first I will tell you that sometimes what is done is that some brush shift is given to the machines to facilitate the commutation process in a better way. For example, what I mean to say is this. So, go to next new page. Here, is this the page? Lecture 74. For example, if you have a DC machine like this, and let it operate as a generator S, and this is north pole. Yoke I am not showing, it is there, and here the brass axis is there. And if the generator direction of rotation is like this in RPS, then these conductors will have induced voltage as well as direction of the current. Under the south pole, it will be all dot. Not? So, that electromagnetic torque becomes opposite to prime mover torque, and these are cross. This is what we have seen, clear? Generator mode. Now, in this case, the armature MMF, whatever will be acting, will be along the Q axis, is not? This is cross dot. So, field will be acting in this direction, armature MMF. and in the quadrature axis the reluctance is high. So, the corresponding flux will be less, that is a good thing, but armature MMF will be acting like that, and this is called cross magnetization. And I told you this is the geometrical neutral plane was defined as the main field axis is horizontal, perpendicular to that is the geometrical neutral axis. And also the magnetic neutral axis coincides with this in this case, when armature is not carrying any current. Now, what is done is this: to have better commutation, sometimes the and all the armature MMF is of cross magnetization. Cross magnetization. That is perpendicular to the direct field axis. So, flux gets distorted, this side it will be higher and so on. So, now what is done? Brush shift. A little brush shift from the usual position of the brushes is sometimes given to the machine. What for? Let us see. Suppose what you do, the same generator, it is acting as a generator. This is the normal position of the brushes and these are the field axis. And this is suppose south, north. This is the direction of rotation n for generator mode. Now, the brushes, instead of placing it here, what is done? Brushes are given a shift by some angle beta electrical. Mind you, it is the representation of a multipolar machine, because under 2 pole same thing is going to happen. So, people prefer to always draw a 2 pole diagram and showing all the angles to be electrical, that should be cleared in mind. So, beta E electrical is the brush shift. So, brush is placed here. In case of generator, brush shift is given along the direction of rotation. The reason we will easily understand right now. So, this is the thing, and these are the conductors, armature conductors. Suppose a little brush shift is given. Now, these conductors, many of the conductors here, most of the conductors are under the influence of the south pole, that will dominate, and few conductors might have gone to the north pole. Particularly the conductors which will be undergoing commutation. That is, I am training this conductor about what lies ahead already. So, it looks like commutation process will be easier. So, however, the currents in the conductors, they are all in series. So, up to this point it will be dot. I am not telling the induced voltage here is 1 second dot, in this portion I am confident dot dot dot, but the current is delivered by the machine, and few turns which has going to under north pole influence, they has to carry same current. Similarly, currents here will be cross. Up to this point cross, and here is the conductor which passes this magnetic neutral axis. It will be the quadrature axis now is, this is the quadrature axis, it is now shifted here. So, you give some brush shift. Under this condition, why brush shift I have given? I have given because the conductor's induced voltage under south pole is of dot polarity, but I am, and this conductor is going commutation, its current will switch over from plus I to minus I as it crosses this brush position. Therefore, I will say that this conductor is started inducing voltage which will be dictated by this north pole a little earlier when it crosses the brushes. These conductors are under the influence of north pole, these are under south pole, like that, and this conductor is under no poles, that is fine. But the current will be here, here perhaps the induced voltage is 0, but these are all series, current has to be same, no doubt. So, it will be like this. Now, under this situation, you find that the armature MMF will be not along vertical, but along this line. This will be armature MMF. And we can easily see this armature MMF will have two components. One is along the d axis, another is along the quadrature axis. It will be like this. Now, lines of force here, south pole, it is like this. Therefore, we find the there will be a direct demagnetization now taking place. There is a component which will directly try to oppose the stator pole strength, which was not the case here. There was all quadrature component, here the components were quadrature. It distorted the flux, no doubt, quadrature component only, but here it is having both direct and quadrature component, this armature MMF. Therefore, there will be a direct reduction in flux per pole, not because of saturation, this that a little drop in flux per pole, not like that. The moment you shift the brush to have better commutation, the moment you do it, I will say, oh, there will be now some component of armature MMF acting in opposite direction of the field flux, because armature MMF flux will be like this, which is directly opposing these lines of force, and there will be a quadrature component. These two components will be there. Now, what people do is this, how to estimate how much is demagnetization and how much is cross magnetization. What you do, you draw another line here such that you imagine this line such that it is also beta E. You imagine another line, this is beta E, same as the electrical beta here. So, that this angle will become 2 beta E, and people then say that the conductors in this 2 beta E and in this 2 beta E will give you the direct axis ampere turns produced by armature. this forget about this one, these conductors and these conductors cross 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 dot 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 spanning over 2 beta E here, 2 beta E here. What is the direction of the flux? Horizontal. So, by considering this group of conductors here, from that I will be able to calculate how much is the demagnetizing ampere turns. So, it is called ampere turns demagnetizing. Similarly, the conductors in this and in this portion, this cross and this dot will produce MMF as if in the quadrature axis, and that is that will fairly give you the idea about the quadrature component of the armature flux. In this case, what was there? All was quadrature. How did I calculate armature MMF? IAZ by 2 AP like this, is not? There was no direct confrontation with the stator flux, it was not doing that, but it was only deforming the armature MMF. But here when some brush shift is given in case of generator in the same direction of rotation, beta E is the angle I know from the normal position of the brushes. I have given a shift beta E electrical degree. Then I will draw a line, another beta E here. Then I see that this is dot, this is cross, and this MMF which are lying in this 4 beta E angle will be along this direction, directly in opposition with the direct axis flux. And it is these conductors which will be responsible for computing how much is the demagnetizing ampere turns per pole we will calculate. Similarly, this conductor cross and this conductor dot will give you the quadrature axis like this. This is how the computation is to be carried out. Now, the calculations are pretty simple. Z is the total number of conductors, Z. So, I will write straight away because we have some idea how to write over 360 degree mechanical degree, 360 degree mechanical angle, this angle is mechanical. Number of conductors present is Z, no doubt about that, total number of armature conductors. Then I have to calculate how many conductors are present in these 4 beta E angles. So, 4 beta E converted to mechanical into 2 by P. How 4 beta E comes in? How many conductors which will produce demagnetizing ampere turns per pole? My goal is to calculate that. It will be then Z by 360 degree. This is also in degree. So, beta E, let me write beta E is the brush shift angle in electrical degree, because all angles I will show here electrical, you must understand. So, how many mechanical angles it means? It means 2 by P, P is the number of poles of the machine. So, Z by 360 into 8 beta E by P. If I make a mistake, point out. So, this is like this. and this is equal to 2z beta E divided by 4 you multiply 90 p, it will be like this. So, this is conductors placed in this angle. How many turns? Turns. You divide it by 2, this will make 1 turn, this will make 1 turn. So, turns present over this angle is z beta E by 90 p, is not? This will be the speed. So, this is turns, turns. Therefore, ampere turns demagnetizing will be current flowing through the turns, that is I A by A, into this one z beta E by 90 p, and this ampere turns will be in these 2 air gaps, it will be dropped. So, per pole it will be half of this. So, this will be I A z beta E by 180 A p. This will be the thing. If beta is equal to 0, no demagnetizing MMF, that is here beta E here 0, I have not shifted the brushes here, you get the same beta is 0 0. How much will be the cross magnetization? That we will calculate also from this. So, this is ampere turns, demagnetizing ampere turns per pole I A z beta E. While using this formula, remember beta E is the brush shift given in electrical degrees, whatever it is, suppose 2 degree, a small brush shift is given. Okay. Now, the question is how much will be then the cross magnetizing per pole. Now, I will not once again calculate like this, because this is for, so the conductors are spanning over 2 beta E, 2 beta E, 4 beta E angle. So, what should be done is this one, cross magnetizing MMF will be calculated because of these conductors, this red marks I am doing now, because of these conductors and because of these conductors, because it is indeed, it looks like this is the cross magnetization. Only this red cross dot conductors will be responsible for that. So, here the thing is it is like this, I will separately draw here, so that this figure does not become very clumsy. What I am trying to tell is, suppose this is your some circle here, okay, this was this, and we have this sort of thing, this is 2 beta E electrical degree, this is also 2 beta E. This is beta E, this is beta E. So, this angle is 180 minus 2 beta E. So, this I write it as this angle is 180 minus 2 beta E, all angles electrical. Therefore, and here are the conductors, for which I have to calculate. And these are all dot, and while calculating cross magnetizing, I do not have to consider this I have already considered for demagnetization. So, these are cross. These are all cross here. I am sorry, this will I will not consider. Is not that this is the thing. Now, in the formula beta E comes, should I derive another new formula? No, for this angle if you know over which the conductors are sprayed, you just substitute there. So, in this case this angle will be half of that, is not, that is this angle will be 90 minus beta E, half of this. So, ampere turns demagnetizing per pole is this one. So, I now write with a different color is that ampere turns cross magnetizing per pole, I have to calculate per pole, will be simply replace beta E by 90 minus beta. These calculations are okay now, 180 minus 2 beta E by 2, because this angle is this, half of this angle. So, it will be then equal to I A Z by 180 A P. Only for beta E I will write 90. Degree writing is not necessary, because numerator degree denominator degree, that goes 90 minus beta E. This will be the cross magnetizing ampere turns. Is that clear? If you add these two, so ampere conductors, if you add these two, then total 80 per pole will be how much? This plus this. If you add these two, it will be equal to IAZ by 180 P, AP comes common, 180 AP, and if you add these two, beta E goes and only 90 will be left. So, it is equal to IAZ by 2 AP as expected, total ampere turns per pole. Therefore, total ampere turns per pole is known. How much of it is demagnetizing is this one, and how much of it is cross magnetizing is this one, is not. I will be able to calculate that. And what should I do if brush shift machine is being used? Then demagnetizing portion of the ampere turns I will try to get rid of using some coils which will produce flux along this line, and the quadrature axis component of the flux by interpole. You know, I will cross magnetizing ampere turns I will calculate. Cross magnetizing is this. If I want to nullify that MMF, I will put some interpole there also. Similarly, the demagnetizing ampere turns this way, if I want to reduce its effect, I have to perhaps what should I do? Compensating winding. So, compensating winding may be used, or in some machines, you know, compound machines, where there will be, apart from series field, some shunt field, there will be an additional field, and that will also try to nullify that. We will come to the compound machine later, but what I am telling, we have learned how to calculate how much with a brush shift here, how much is the cross magnetizing ampere turns per pole and how much is the demagnetizing ampere turns for a small brush shift angle. Do not give brush shift to a large amount. And also note that this brush shift angle for generator is to be given along the direction of rotation. What if somebody generator mode, if somebody gives here the brushes, he puts it here, what is going to happen? The opposite thing is going to happen. That is, this conductor which is undergoing commutation will be still under south pole, you know, direction of rotation is same. So, one should be very careful while giving a brush shift. For generator it should be like this, and obviously this everything remains same. For generator the direction of rotation is this. For motor mode, just show the direction of rotation there, dot cross, everything will remain intact. And you see, for generator mode, brush shift is to be given opposite to the direction of rotation. We have shown that now. In case of, once you have shown the current direction, field poles, polarities for a generator with a assumed direction of rotation, the same diagram can be used to tell you things about motor mode. Only thing, then you erase this direction of rotation, show this to be the direction of rotation, right is motor. That is what I am telling, same diagram. This is for generator mode, direction of rotation, this is for motor mode, direction of rotation. I think you have got this idea. So, this is here I will stop talking about armature reaction and things like that for the time being. And now I will take up some problems can be solved from Parker Smith's book, that is, for a given DC machine, what should be the ampere turns per interpole, or how much is the cross magnetizing ampere turns needed in this case. You kindly try to solve this problem, which I will also put in the problem sheet there. But here the important point is that the segregation of this conductor is done rather arbitrarily. Arbitrarily in the sense, by looking visually to it, I just attribute beta E, then 2 beta E here, 2 beta E here gives you the demagnetizing component. And this 180 minus 2 beta E and 180 minus 2 beta E here will give you cross magnetizing ampere turns pole. Henceforth, we will take some regular and rather usual stuff, that is I will discuss about now motors and how to calculate torque, power, about speed control, braking, those are very interesting stuff. Thank you.